Okay, let's get right into it. We keep hearing about AI models getting bigger, smarter, more powerful, but what if the very foundation they're all built on has a major fundamental flaw? Well, today we're going to talk about a new paper that proposes a really elegant solution. It's called log linear attention, and it could completely change how AI thinks on a massive scale. So, deep down, inside models like GPT, there's this core concept called the attention mechanism. You can think of it as the magic that lets an AI understand context. It's how it knows that when you say it, you're talking about the ball, not the box. It's the engine that's been driving this whole revolution. But it turns out that that engine has a serious problem, a really critical flaw that gets worse and worse the bigger we try to build these things. It's created this bottleneck that's been holding AI back from understanding truly huge amounts of information all at once. And that brings us to the heart of the problem we're going to unpack today, the attention bottleneck. And just to be clear, this isn't some small, minor bug. It's a fundamental mathematical barrier that's been a huge headache for researchers. This image right here, this shows you everything you need to know about the problem. Standard attention is an all-to-all system. Now, to get why that's a bad thing, imagine you're at a super crowded party, and to understand what's going on, you have to listen to every single person talking to every other person, all at the same time. It's just chaos, right? And it gets exponentially crazier with every new person that joins the party. In the world of computer science, this incredibly expensive, chaotic relationship has a name. It's called O of t squared, or as it's more commonly known, quadratic complexity. So what does that actually mean in plain English? It means if you double the length of a document you want an AI to read, the computer power and memory it needs doesn't just double, nope, it quadruples. Double the text again, and the cost balloons by 16 times. You can see how this just gets out of control fast. It makes it wildly expensive and pretty soon physically impossible to process something like a whole book, a massive code base, or a huge stack of research papers in one go. Now, this isn't a new problem. Researchers have known about this for a while and have been trying to fix it for years, but every solution so far has come with a really difficult trade-off. You see, for a long time, researchers were stuck between a rock and a hard place. On one hand, you had the standard method, what's called softmax attention. It's super powerful, really good at understanding nuance, but as we just saw, it's painfully slow and a total memory hog. On the other hand, you had alternatives like linear attention, way faster, way more efficient, but it just wasn't as smart. It sacrificed a lot of that power. So you had to choose, do you want power or do you want efficiency? You couldn't have both. That is until now. So let's talk about this new proposal, the log linear idea, which basically tries to give us the best of both worlds. Okay, remember that chaotic spider web we saw earlier? Now, look at this. It's the complete opposite. Instead of every single point trying to connect to every other point, log linear attention is organized. It's smart. It groups nearby info together, and then it summarizes it. It's less like that chaotic party and more like a well-run company, where you get clear memos summarizing what's happening at every level. So how does it pull this off? Well, the secret sauce is this really clever data structure from computer science called a Fenwick tree. Now, you don't need to understand all the deep math behind it. The main thing to know is that this structure is just perfectly designed to create these multi-level summaries in a ridiculously efficient way. Let's just break it down into 3 simple steps. It's actually a beautiful concept. First, the model takes nearby bits of information, or tokens, and clumps them into small groups. Step 2, it creates a quick summary of each of those little groups. And then, and this is the brilliant part, it just repeats the process. It takes those summaries and groups them together to create higher-level summaries, and so on and so on. It's this clever hierarchical approach that totally smashes that quadratic bottleneck. Okay, so the theory sounds fantastic, right? But does it actually work in the real world? Let's take a look at the results from the paper, because this is where it gets really exciting. And the answer is a huge, resounding yes. Check out these charts. They're comparing a model using log linear attention against other top-tier methods. On the left chart, higher is better. That's training speed. And look who's winning. On the right, lower is better. That's how long it takes to run, and again, it's not even close. The log linear approach is the clear winner. It's not just a little bit better, it's practically faster and way more efficient. But here's the killer question. Does all that speed make the model dumber? Did we just trade smarts for efficiency? Absolutely not. Look at this. When you take existing models and swap in log linear attention, their scores on common sense reasoning tests stay right up there with the big, powerful models. In some cases, they even get a little bit better. So you get all that speed and efficiency without sacrificing the smarts. It's the whole package. And this, right here, this might be the most impressive test of all. It's called the needle in a haystack test. You basically hide one tiny fact, the needle, inside a massive document, the haystack, and see if the model can find it. And the results are just incredible. The log linear models find that needle with almost perfect accuracy, even when the haystack gets insanely long. This proves they're not just skimming the long text, they're actually understanding and remembering what's inside. So let's zoom out. What does this all really mean? This isn't just a small incremental improvement. This feels like a fundamental shift in the architecture, one that could open up a whole new world of possibilities for AI. So what's the bottom line here? Why does this matter to you? Well, by finally breaking that quadratic bottleneck, we're giving AI the ability to think so much bigger. We're talking about models that can read and understand an entire novel, a company's entire software codebase, or decades of legal documents, all in a single pass. This is going to make powerful AI cheaper to run, more accessible to everyone, and it could unlock applications we've only dreamed of in science, medicine, law, you name it. And that's really the thought I want to leave you with today. This isn't just about making chatbots that can handle longer conversations. This is about enabling a whole new scale of machine intelligence. So just think about it. What kind of problems could we solve if an AI had the power to read, remember, and reason over the entire collected knowledge of a library? The future just got a whole lot longer.